The number of industrial robots working in factories hit, what was it, 2.7 million globally back in 2020?
An incredible number. And it's not just growing steadily, it's rocketing upwards exponentially.
Right. And this isn't just about more machines doing repetitive tasks. It's a total reimagining of how industries function. Data, connectivity, intelligence, they're absolutely at the core now.
Mm-hmm. So this deep dive is really designed to be your, let's say, quick but thorough guide. We want you to understand the technologies, the really fascinating, sometimes unexpected ways they're being used, and of course, the big challenges shaping the factories and systems of tomorrow.
And our mission here really is to unpack how all these different technologies, we're like digital copies of things, robots working with people, hyper-connected devices, how they're making whole systems basically think for themselves, anticipating what's needed, reacting fast.
And it's not sci-fi. This is happening now.
Right now, across the board.
Yeah, and the range is just wild, isn't it? We're going to touch on healthcare, how you shop, massive manufacturing stuff, and even like spacecraft.
It pops up in some surprising places.
It really does. Okay, so let's start right at the beginning. Industry 4.0, what is it? What's the big idea behind this fourth industrial revolution everyone talks about?
Okay, so at its heart, Industry 4.0 is this incredible merging of the physical world and the digital world. Think about a factory floor. But instead of just machines doing tasks, they actually know what's going on around them. They're talking to each other constantly, adapting. And that leads to these smart factories. They're super flexible. They can customize things like crazy. And they're way better with resources. It's a total rethink of production.
Okay. Flexible and efficient. What makes that possible? What are the building blocks?
The real foundation. It's something called cyber-physical systems, CPS for short.
Right.
Think of them as like intelligent agents. They blend physical processes, a machine running with these really sophisticated computer models, these computational brains. And what's really transformative about CPS is they can understand their own state, their own condition. They can even manage their own maintenance, sort of.
Self-aware machines almost.
In a way, yeah. Self-awareness and self-maintenance capabilities. You see them everywhere. Controlling processes and power plants, managing advanced medical tech, complex automation systems.
Got it. So CPS are the smart entities. But how do they all talk? You mentioned machines communicating. That sounds like the Internet of Things, right? But for industry.
Exactly. You often hear about the Industrial Internet of Things, or IoT, alongside Industry 4.0. And they fit together perfectly. If you think of CPS as the brains and the muscles,
okay,
the IoT is like the nervous system. It's this huge network. All the machines, sensors, components, they're all connected, all sharing data easily. It's the communication backbone that lets all those smart CPS devices actually work together, share info, coordinate what they're doing.
So that connection unlocks the real power.
Absolutely. Yeah. When you combine Industry 4.0 thinking with the IoT, that's when you see the big leaps. Huge jumps in productivity, the ability to do mass customization, unique products, but made efficiently. Much faster production speeds, and better, more consistent quality, too.
Yeah.
We move from rigid lines to these really agile, responsive operations.
Wow. Okay, that sounds incredibly powerful, like a super nervous system, as you said, for industry. But with that much connection, all that data flying around, surely there are some big challenges, some hurdles to jump. It can't all be smooth sailing.
You're absolutely right to ask that. The potential is massive, but yeah, there are definitely critical challenges. For one, security. Just having so many connected devices creates a much bigger target for attacks. You need really strong defenses.
Makes sense.
There's power consumption. These networks can use a lot of energy. Interoperability is another one, getting systems from different makers to actually talk the same language.
Right, the compatibility issue.
Yeah. And potential communication delays. Even tiny delays can matter in real-time control. Plus, beyond the tech, there's the people side. Do we have the skills? Is the basic IT infrastructure good enough? These are real obstacles. Poor IT infrastructure, inadequate human resources. These things need addressing.
Okay, so we have these smart connected machines, but how does all that data actually become intelligent? You mentioned intelligent analytics. That's the key piece, right? Making sense of it all.
Precisely. It's not just about collecting data, it's about analyzing it effectively. And you're right, we want to focus on what this achieves, not get bogged down in the complex AI algorithms behind it.
Right, so how does that intelligence play out in the real world?
Well, it all starts with collecting just enormous amounts of data. Sensors everywhere, the whole IIoT network, feeding information back. Then advanced analytics get to work. Let's look at healthcare. It's a great example.
Okay.
Advanced machine learning, ML, is playing a huge role there. It's not just about treating sickness. It's about finding diseases much, much earlier. That really improves care quality.
How does it do that?
Well, algorithms, things like support vector machines, logistic regression, they analyze massive patient data sets. They look for really subtle patterns, patterns that might point to obesity, heart problems, even different cancers, often way before clear symptoms show up.
Wow. So spotting things humans might miss.
We're spotting them much sooner, yeah. The benefits are huge. It helps doctors and nurses make, frankly, more wise decisions. They can spot trends faster. It makes medical studies more effective. Ultimately, these smart systems are changing how healthcare is delivered, making it better, more effective, often cheaper, too.
And you mentioned real-time monitoring.
Yeah, that's another powerful piece. Think about cardiovascular diseases, CVD. Tiny IoT sensors can gather physiological data right from the patient nonstop. That data gets analyzed immediately. So you can have remote medical help, critical tracking, alerts in emergencies. It can literally save lives.
That really is shifting healthcare from reacting to predicting and preventing. Incredible. But it's not just these huge life-saving applications, is it? You hinted earlier, many of us bump into this kind of intelligent analytics every day, maybe without even thinking about it.
Oh, absolutely. Every single day. Think about recommender systems.
Ah, okay, like on shopping sites or streaming services.
Exactly. They're designed to solve that classic information overload problem. They act as really smart filters for us. You browse Netflix, right? Those shows it suggests. Not random. It's complex systems, predicting what you'll enjoy based on what you watched, what similar people watched.
Right. It knows me too well sometimes.
Doubles, doesn't it? Or think about a big retailer like Walmart. They analyze enormous amounts of purchase data to spot trends. That helps them decide what products to suggest, even where to place things in the store. Any e-commerce site relies on this, helping you find stuff you actually want, but might never stumble across in their massive catalogs. They look at your past buys, your preferences, and try to connect the dots for you.
Okay, so these analytics are influencing healthcare or shopping. Now, what about this idea of a digital twin? You mentioned creating virtual copies. That sounds fascinating. How does that fit in?
Digital twins are, yeah, they're really cool. Imagine creating a super detailed, dynamic virtual model of a physical thing. It could be a single product, a whole production line, even an entire supply chain.
Dynamic, meaning it changes.
Exactly. It's not just a static 3D model or blueprint. It's constantly fed real-time data from its actual physical counterpart out in the world. So the virtual twin mirrors the real thing, moment by moment.
Okay, that's a powerful concept. What do you do with that?
All sorts of things. They're fundamental for developing those cyber-physical systems we talked about. You can use them to predict and optimize how a new product design will work before you build it. You can use them to fine-tune production processes for maximum efficiency. They can even help predict, say, unprecedented events or disruptions somewhere in your supply chain, giving you a heads up to react.
So, like simulating problems.
Simulating problems, testing solutions, yeah. Plus real-time monitoring of quality, performance, even tracking goods during transport. And think about sustainability. You can use the twin to analyze resource use, figure out better ways to recover materials.
And risk.
Huge for risk management, that predictive maintenance idea we touched on. Digital twins are perfect for that. Simulate potential failures in the virtual world, figure out when maintenance is needed before the real thing breaks down, avoids costly failures.
Okay, so the digital twin is the virtual plan, the simulation. Where does this intelligence then, like, physically manifest? Where does it meet the real world on the factory floor, for instance? I guess robotics comes in here.
That's often the case, yes. Advanced robotics is where a lot of this digital intelligence translates into physical action. And robots today are way beyond those old, clunky, single-task arms.
Right, they've evolved a lot.
Dramatically. We've gone from simple machines to these really complex multi-axis robots that can have interchangeable grippers, different tools, makes them incredibly versatile. Plus, they can work in tough spots, harsh environments, physically demanding jobs, places humans maybe shouldn't be.
And what can they do?
Astonishing things, really. Highly repetitive tasks, sure, but also incredibly complex ones with amazing precision. Think high-precision welding or spotting microscopic flaws in materials. That boosts quality and overall effectiveness.
But aren't robots replacing human jobs? That's always the concern.
That is the concern, and it's a valid discussion. But a really exciting development is cobots, collaborative robots. Yeah. These are designed specifically to work with human workers safely, side by side. They're not there to replace people, but to assist them. The whole principle is that human intelligence, human intervention, it's still key. The goal isn't replacement. It's humans and machines working together, leveraging each other's strengths, tandem work.
That's a really important distinction. Humans and machines collaborating. Okay, so we have the intelligence, the virtual models, the robots. But none of this happens without communication, right? All these things need to talk, share tons of data seamlessly. That must be a huge challenge in itself.
It's absolutely crucial. It's the invisible backbone. And yes, routing all that big data around the IoT efficiently requires a whole mix of communication tech. You've got familiar stuff like Bluetooth, low energy, BLE, Zigbee, Wi-Fi, but also specialized protocols designed just for these low-power, often large-scale networks.
Anything particularly interesting standing up there?
Well, one technology that's getting a lot of attention for certain IoT jobs is LoRaWAN, long-range, wide-area network.
LoRaWAN. Okay, what's special about it?
It's a unique combo. Ultra-long range, really low power use, and pretty minimal costs. So it's perfect when you need to send relatively small bits of data over a really long distance without draining batteries or breaking the bank.
Like what kind of application?
Think smart cities or industrial monitoring. Real-world tests have shown it covering like well over 10 kilometers in urban settings. Or imagine reading utility meters, water, gas, electricity that are buried deep in a basement somewhere. LoRaWAN can often get that signal out reliably.
That's pretty impressive for low power. Okay, so communication is sorted, but we talked about challenges earlier, and the big one lurking behind all this connectivity must be cybersecurity.
The elephant in the room, yes.
With everything connected, everything sharing data, how on earth do you protect it all? How do you secure these critical systems?
It's arguably the most critical challenge for Industry 4.0 because the wireless network area has just exploded, and the use of devices moving around, the in-motion device network usage, is growing rapidly. All that creates a much, much bigger surface for attackers.
And what kind of attacks are we talking about?
Oh, a whole range. Nasty stuff. Botnets, hijacking lots of devices for attacks, data spoofing, feeding fake data into systems, eavesdropping, obviously, ransomware, locking up critical systems, social engineering trying to trick people, denial of service, distributed denial of service, basically flooding systems to shut them down.
DDoS.
Man-in-the-middle attacks, intercepting communication, injecting false data to cause chaos or wrong decisions. The list is long.
Scary stuff. So what's the defense strategy?
A big part of it is data leakage prevention, or DLP. You have to stop sensitive info from getting out or being corrupted. Key tools here are things like encryption, scrambling the data so only the right people or systems with the right keys can read it. You have both symmetric and asymmetric key methods, and also message authentication codes, MACs. These verify that a message hasn't been tampered with and that it really came from who it says it came from. It's all about maintaining confidentiality, authenticity, and integrity. Crucial. Some systems even use things like a Centroid-based document classifier to help automatically spot and protect sensitive data.
Okay, so a multi-layered defense is essential. Now, connecting this back to the bigger picture, we've seen factories, healthcare, shopping. Where else is this heading? Are these intelligent systems pushing boundaries even further, maybe, off-planet?
It's definitely pushing boundaries, and yes, even into space. Think about Earth's orbit. It's getting crowded up there. More satellites, more space junk.
Right, space debris is a growing problem.
A big one. And it increases the risk of collisions, which can be catastrophic and expensive. So there's research and development into concepts like a spacecraft anti-collision system, SES.
Okay, an anti-collision system for space. How would that work?
Well, the designs involve several key parts. There's a traffic identification design, maybe using IoT-connected cameras to actually spot objects near the spacecraft. Then, a density evaluation model to figure out how crowded that patch of space is. And finally, a safe trajectory planning model to calculate the best path to steer clear of trouble.
So it spots danger and plots a way around it.
Essentially, yes. But what's really interesting is how it often integrates the human element. Some designs include a heads-up display, a HUD system, right in the pilot's view.
Like in a fighter jet.
Kind of, yeah. It displays critical info, warnings, and maybe even recommendation strategies for the pilot to choose, suggested maneuvers. But, and this echoes the cobot idea, the ultimate decision rests with the human pilot. The system advises, it recommends, but the person makes the call. Even in space, it's about augmenting human judgment, not replacing it.
That human-machine collaboration theme again. Fascinating.
Did you know the number of industrial robots working in factories hit, what was it, 2.7 million globally back in 2020?
An incredible number. And it's not just growing steadily, it's rocketing upwards exponentially.
Right. And this isn't just about more machines doing repetitive tasks. It's a total reimagining of how industries function. Data, connectivity, intelligence, they're absolutely at the core now.
So this deep dive is really designed to be your, let's say, quick but thorough guide. We want you to understand the technologies, the really fascinating, sometimes unexpected ways they're being used, and of course, the big challenges shaping the factories and systems of tomorrow.
To really appreciate the scale and, importantly, the speed of Industry 4.0, we need a quick look back. How did we actually get here? It's about this march of industrial revolutions. Each one fundamentally changed how we make things.
Totally. So let's rewind back to the 18th century. That's Industry 1.0, mechanization.
Steam power.
Exactly. Steam power. A massive shift from, people making things by hand, artisan style, to machine-centric factory production. Think early textile mills, locomotives.
Yeah.
The birth of the factory system.
Bringing power, mechanical power, to production.
Yeah.
Making things scalable for the first time.
It absolutely redefined work. Then building on that, we get Industry 2.0, late 19th century.
Electrification.
Yeah.
This was huge. Widespread electricity allowed for things like assembly lines, mass production.
Henry Ford's Model T rolling off the line. That's the image, isn't it? Making cars accessible.
And electric motors in factories, railways expanding, telegraph, telephone.
Yeah.
Shrinking the world, speeding things up.
Though it also ramped up fossil fuel use. CO2 emissions started to climb. A challenge we're still dealing with, obviously.
Definitely. Which brings us then to the third industrial revolution, sometimes called the digital revolution or automation. Mid-20th century, maybe starting around the 1960s.
Yeah, that sounds right. This was about computers entering the scene. Early computers, programmable logic controllers, PLCs controlling machines, and the first real industrial robots.
General Motors, wasn't it?
Yeah.
In 1961, they introduced the first industrial robots, kicked off that era of high-level automation.
And the dot-com boom later, ICT, information and communication tech, really taking off, starting to change how complex parts were made, even early 3D printing ideas.
And now here we are, Industry 4.0. What's striking is the pace. Unlike the others, which unfolded over decades, this one feels exponential.
It really does. It's defined by this incredible convergence, this blurring of lines between the physical world and the digital world.
Driven by just massive amounts of data being generated and the need to find meaning in it all, actionable insights.
So analytics, in this context, isn't just a nice-to-have tool, it's the engine, the key to transforming manufacturing and, honestly, almost every other industry, too, making digital and physical almost inseparable.
So what really defined it? What are the pillars setting it apart?
Okay, first pillar, maybe the most fundamental, cyber-physical systems, CPS.
Right. This is where the physical stuff, the machines, the process on the factory floor get deeply integrated with computation and networks.
It creates this seamless feedback loop, doesn't it, between the physical environment and the logical digital layers.
Exactly. We're moving beyond machines that just do things to machines that, well, think, learn, respond intelligently.
So how do you design these incredibly complex systems? I know there's a framework.
Yeah, the 5C architecture, it's a conceptual guideline, really. Helps break down the workflow of a CPS into 5 key levels. How they gather data, process it, make decisions, and then act. That closed loop idea.
Okay, level 1, the first C.
Smart connection. This is the base layer. All about how machines, sensors, components actually acquire and then transfer accurate data from the physical world.
So like tiny sensors in a robot's joints constantly sending data, temperature, vibration, stress.
Precisely. It's the digital nervous system, gathering that raw information, capturing reality digitally.
Got it. Second C.
Data to information conversion. This is where the analytics really start to kick in. Taking that flood of raw data and making sense of it, turning it into meaningful, actionable information.
Using sophisticated data mining, machine learning,
Yeah.
finding the patterns, the correlations.
Right, like taking those raw temperature and vibration readings and turning them into, say, a clear health score for the machine.
Yeah.
Or even an early warning, hey, something's about to go wrong.
Okay, makes sense. Third C.
Cyber. This is the central hub. Often a distributed network, lots of computing power. This is where the main intelligent analytics happen. The heavy lifting of processing, modeling, analysis.
The brain of the operation, so to speak. Running the algorithms, generating the raw insights.
Yep. Which leads directly to the fourth C, cognition. This is where the system moves beyond just processing data to actually understanding it, grasping the meaning.
So generating deeper insights, making predictions.
Exactly. Developing a kind of self-awareness or foresight. Spotting subtle trends, forecasting potential issues, understanding complex relationships a human might easily miss. Turning analysis into real intelligence.
And the final piece of the loop, the fifth C.
Configuration. This is the crucial feedback step. Taking those insights from the cybercognitive layers and feeding them back to the physical world, enabling self-adjustment, self-configuration, adaptation.
So the system can automatically tweak machine settings for better performance, or even prevent a predicted breakdown.
Precisely. Or imagine a whole factory line reconfiguring itself automatically to produce a unique, customized product based on a new order, all without direct human intervention at that stage.
Wow, okay, so CPS is fundamental. What's the next pillar?
The Industrial Internet of Things, or IIoT. This
Yeah.
is basically taking the concept of the Internet of Things, your smart thermostat or speaker at home, and applying it specifically to industrial settings.
So connecting machines, sensors, devices within factories, power grids, supply chains, letting them all talk to each other and share data.
Exactly. Everything from tiny sensors on a production line communicating with the robots up to entire fleets of autonomous delivery trucks coordinating their logistics. Massive interconnectedness.
And that needs robust communication tech, right? Industrial environments can be tough.
Absolutely. IoT uses a whole range of technologies. Things like Bluetooth Low Energy, BLE, for short-range, efficient connections between devices. Zigbee is great for creating mesh networks into factory devices, relay signals extending range and coverage.
Standard Wi-Fi obviously plays a role for local networks.
Of course. But for really seamless, reliable connections, especially over larger areas or with many low-power devices, you see protocols like IPv6 and 6LoWPAN. They're designed for efficiency, handling huge numbers of addresses and managing energy use in these vast networks of tiny sensors.
Okay, so we have CPS and IoT as pillars. The promise here sounds enormous. What are the big advantages people are seeing?
Several key benefits stand out. First, huge gains in productivity and efficiency. Predictive maintenance means moving towards near-zero unplanned breakdowns. Operations become much smoother, saving companies potentially millions in lost production.
And that allows for much greater flexibility and mass customization, right?
Definitely. Industry 4.0 makes it feasible to produce highly personalized products, tailored down to individual customer specs, but still at reasonable costs. A consumer orders something unique, and the system adapts on the fly to make it.
Which also implies improved quality and speed, pinpoint accuracy from automated systems, faster production cycles.
Absolutely. And beyond the factory itself, it enables entirely new business models. We're seeing shifts towards direct customer interaction, companies offering services wrapped around products.
Like the product as a service idea. Instead of buying a jet engine, an airline pays for flight hours, and the manufacturer guarantees the uptime using predictive maintenance.
Exactly that kind of thing. All enabled by this constant stream of data and intelligent analysis.
But it can't all be smooth sailing. This kind of massive transformation must come with challenges.
Oh, absolutely. Big ones.
Yeah.
Top of the list for many is security vulnerability.
Makes sense. Connect everything and you create a much bigger target for attacks.
Precisely. The attack surface expands dramatically. It's a huge concern in design and operation. We're talking data theft, espionage, ransomware holding operations hostage, even physical disruption.
Like the Stuxnet example people often mention, a cyber attack causing physical damage to industrial equipment.
Exactly. It showed the terrifying reality of cyber-physical threats. The stakes are incredibly high.
What else?
Power consumption and energy constraints. Every single connected sensor, every device uses energy. Especially for battery-powered sensors spread across a factory or a remote site, managing power for long life is critical. Designing for low-power operation is key.
And interoperability. Getting devices and systems from different vendors built on different standards to talk to each other seamlessly, that sounds like a nightmare.
It's a major headache. Lack of common standards, proprietary protocols. It hinders data sharing and full integration. You spend a lot of time just trying to make things compatible.
Which probably leads to issues like communication delay and quality of service, QoS problems. In real-time control, delays are bad news.
Very bad news. Even milliseconds can matter when controlling high-speed machinery or coordinating robots. Ensuring reliable, timely data flow is absolutely critical for safety and efficiency.
And the human side.
A huge challenge. The human resources and skills gap. Industry 4.0 requires a workforce with totally new skills. Data science, AI, robotics programming, cybersecurity. There's a real shortage and an urgent need for training and upskilling. We need people who can work with these new systems.
Okay, that gives us a good grounding. Now let's dive into the specific core technologies making all this happen. Where should we start? Maybe digital twins.
Sounds good. Digital twins, DTs. This is one of the most fascinating concepts, I think.
It really does sound like sci-fi. A virtual copy of a real thing.
Essentially, yes. It's a dynamic virtual model or simulation of a physical product, a process, even an entire system like a factory. The key is dynamic. It's constantly updated with real-time data from its physical counterpart.
So the physical machine and its digital twin are connected, constantly sharing data, learning from each other.
Exactly. This allows the digital twin to mirror the state of the physical asset and, crucially, to predict future behavior, simulate what-if scenarios, and optimize performance in the real world before you actually implement changes physically.
That's powerful. So they're used for what? Improving product quality, monitoring processes?
Many of the above. They're crucial for transforming internal structures. Better quality, enhanced monitoring, reducing uncertainty. They bridge that gap between the design phase and actual manufacturing. You can test and optimize virtually first.
So applications, product design and optimization seems obvious. Test designs virtually without building physical prototypes.
Precisely. Find flaws, predict performance, optimize efficiency much faster and cheaper, accelerates the whole design cycle.
What about supply chain optimization? That seems complex.
It is, but DTs can model an entire supply chain. This lets companies test strategies for resilience, figure out how to handle disruptions like we saw with COVID, simulate demand spikes, supplier issues, find bottlenecks, plan alternative routes.
Interesting. And sustainability, how do they help there?
By modeling resource use, a DT of a factory can simulate energy consumption, water use, waste streams, test different scenarios to improve resource efficiency, optimize recycling, make sustainable ideas more concrete using data fusion and ML.
And intelligent risk management, predictive maintenance, we touched on that.
Yeah, this is a huge one. DT's predicting equipment failure before it happens, like a twin of a jet engine monitoring its health in real time, flagging a part that needs replacing soon. Or even in healthcare, simulating patient responses to treatments.
So what makes these digital mirrors tick? It must be incredibly data heavy.
Hugely data intensive. Requires constant real-time monitoring from sensors, seamless integration with cloud computing for storage and processing power, and advanced data analytics tools. They're constantly being fed information.
But there must be challenges too.
Definitely. Data standards and consistency are big ones. Getting high-quality, compatible data from diverse sources is tough. High processing requirements, these models need serious computing power. And, of course, privacy and security risks, managing all that sensitive operational data securely.
Okay, let's move to robotics. We mentioned the early GM robots. They've come a long way.
A very long way. From those simple, fixed-task arms to today's incredibly complex, multi-axis robots with interchangeable tools, capable of highly precise, intricate work at high speeds.
But the really big shift is collaborative robots, or cobots, right?
Absolutely. That's the game changer. These aren't the robots locked away in cages anymore. Cobots are designed specifically to work safely alongside human workers in the same space without physical barriers.
Fostering that human-machine synergy.
Exactly. Each plays to their strengths. Cobots handle the repetitive, strenuous, or precise tasks, while humans handle the complex decision-making, adaptability, and quality oversight.
The benefits are pretty clear. Productivity, accuracy, profitability. Robots don't get tired. They can work in harsh conditions.
Right. Increased output, fewer errors, often a quick return on investment. They take over the dull, dirty, dangerous jobs, freeing up humans for more valuable roles.
You mentioned different levels of interaction.
Yeah, there's a standard scale. It goes from no collaboration robots fenced off,
Right.
2, coexistence sharing a workspace, but no direct interaction, 3, synchronization coordinated tasks, maybe passing parts, but separate actions, 4, cooperation actively working together on the same task, like a human guiding a cobot. And CFI, full collaboration, truly working in tandem, adapting to each other in real time, using sensors and AI.
And AI is key to that highest level.
Definitely. AI, computer vision, sensors like haptic feedback, allowing robots to feel pressure, enables them to perform much more complex adaptive tasks. Imagine a robot assisting a surgeon, responding precisely to their movements, or in manufacturing, adjusting its grip based on the object's fragility. It enhances that synergy.
Okay, next up, IoT platforms, the middleware piece.
Right. In this huge IoT ecosystem with potentially billions of devices, you need something to manage the connections and data flow. That's where IoT platforms come in. They act as the middleware layer.
Like a universal translator or a bridge.
Good analogy. They bridge the gap between the diverse IoT devices and networks on one side and the applications that need the data on the other. They enable interoperability, abstracting away the complexity of different protocols and technologies, making everything work together.
And they need to be seriously robust.
Absolutely. Key functional requirements include massive scalability, handling potentially billions of connections. Remember that 60 billion devices prediction, plus robustness, high security, seamless data integration, and powerful built-in analytics capabilities.
And non-functional things too, like speed.
crucial non-functional requirements: high performance and real-time responsiveness for critical tasks, good usability for operators, and vital energy efficiency, especially managing power for countless battery-operated sensors.
Are there different types of these platforms?
Yes, different types of middleware focus on different needs. Message-oriented middleware, MOM, is good for reliable asynchronous communication. Object middleware helps distributed software components interact. Database middleware connects applications to various data stores.
And looking ahead, things like 5G and even 6G are important here.
Hugely important. They provide the high bandwidth, super low latency, and reliable connectivity that next-generation IoT applications demand. Think real-time remote surgery, massive autonomous vehicle coordination. 5G, 6G are enablers for the future of these platforms.
Okay, let's talk about the brains, artificial intelligence, AI, and machine learning, ML.
The absolute engine driving so much of this. AI and ML are essential for making sense of the data deluge, spotting patterns humans can't, and enabling those predictive and prescriptive actions, moving from just knowing what happened to predicting what will happen and suggesting what to do about it.
So different types of ML supervised learning is the first one.
Right. Think of it as learning with a teacher. You feed the algorithm data that's already labeled with the correct answer, like pictures labeled cat or dog. It learns the relationship between the inputs and the outputs to make predictions on new, unseen data.
Used for things like predicting machine failure based on past failures or classifying things.
Exactly. Common algorithms are things like support vector machines, SVM, logistic regression, random forests, k-nearest neighbors, KNN.
Then unsupervised learning, no teacher this time.
Correct. You give the algorithm unlabeled data and ask it to find hidden structures or patterns on its own, like grouping similar customers based on purchasing behavior without knowing the groups beforehand. K-means or K-modes clustering are examples. Discovering anomalies.
And reinforcement learning, that's different again.
Yeah, this is learning by trial and error. An agent takes actions in an environment, gets rewards or penalties based on the outcome, and learns over time to maximize its cumulative reward. How AI learns to play games or optimize robotic control or manage complex systems like traffic flow.
Within ML, there's deep learning using neural networks, like CNNs.
Convolutional neural networks, CNNs, yeah. They are powerhouses for image processing. Excellent at feature extraction. That's why they're used so much in computer vision for robots, object recognition, defect detection, navigation.
And for data over time, like sensor readings.
That's where recurrent neural networks, RNNs, and especially long short-term memory, LSTM networks, shine. They have a kind of memory that lets them process sequences, crucial for time series forecasting, predictive maintenance, speech recognition.
There's also GRUs.
Gated recurrent units, GRUs. A slightly simpler, often faster alternative to LSTMs, particularly good when you don't have massive data sets. Still very capable for sequential data.
Okay, so we have these powerful models, but how do we know they actually work reliably? That they're not just good on the training data?
Crucial question. That's where validation techniques come in. Validation is absolutely vital to select the best model settings, the hypoparameters, and avoid pitfalls like overfitting.
Overfitting being learning the training data too well, including noise, so it fails on new data.
Exactly. Or underfitting, where the model is too simple and misses the patterns. Validation helps find that sweet spot.
Simplest way is holdout validation. Just split the data.
Yeah, split into training and testing sets, train on one, test on the other. Simple, but the test set might not be fully representative.
So k-fold cross-validation is better.
Generally more robust. Divide the data into k-folds, trained k-times, each time using a different fold for testing and the rest for training. Averages the performance across all data, gives a more reliable estimate.
And stratified k-fold.
That's important for imbalanced data, like if you're detecting rare defects. It ensures each fold keeps the same proportion of classes as the original data set. Prevents the model being biased towards the majority class.
Okay. And Monte Carlo cross-validation.
That involves multiple random splits into train-test sets, like repeated holdout validation. Gives a good average, but some data might get tested more often than others.
Once validated, you need to measure how well it performs. Evaluation metrics.
Right. Quantifying performance. Common ones are accuracy, simple percentage, correct. But accuracy can be misleading with imbalanced data.
So you need things like precision and recall.
Exactly. Precision is, of all the times I predicted positive, how often was I right? Good for minimizing false alarms. Recall is, of all the actual positive cases, how many did I find? Good for minimizing misdetections.
And the F1 score balances those two.
Yes, it's the harmonic mean of precision and recall. useful when both are important. Then there's area under curve, AUC, often used for binary classifiers, showing how well the model distinguishes between classes.
And for security, things like FAR and FRR.
False acceptance rate and false rejection rate, crucial in biometrics or access control. How often do you wrongly let someone in versus wrongly block someone out? You need to balance those risks.
Phew, okay. That covers AML. Now the infrastructure holding it all together, big data analytics and cloud computing.
The absolute backbone. Industry 4.0 generates unimaginable amounts of data-structured, unstructured sensor streams, logs, images. Traditional methods just can't cope. That's the big data imperative.
And the cloud is the answer.
It's the dominant platform. Scalable, flexible, cost-effective for storing, processing, analyzing these massive data sets. Offers big data as a service, providing the compute power on demand.
Using frameworks like MapReduce and Hadoop.
Those were foundational for distributed processing, breaking big jobs across many computers, now enhanced by tools like Spark for faster, real-time analytics, Hive and Pig for easier querying and scripting.
And databases like HBase, Bigtable.
Right, specialized databases designed to handle the volume and variety of big data efficiently.
And all the major cloud providers offer these services. AWS, Google, Microsoft, IBM.
Absolutely. They offer comprehensive suites, storage, analytics, machine learning tools, data warehousing, making these powerful capabilities accessible. Think of Walmart analyzing shopping trends, or Netflix using viewing data to drive its recommendation engine and content creation. That's big data in action.
But again, challenges, network bottlenecks, cost.
Huge challenges, network hurdles in moving massive data, the ongoing cost of storage and processing, and significant ethical and privacy concerns. How is this data being used? Is it secure? Legal frameworks are constantly trying to catch up.
Which leads us perfectly into cybersecurity and Industry 4.0.
Critically important. All this connectivity and digitalization creates a massive target. Protecting not just data, but physical industrial operations is paramount.
The threat landscape is complex. Cyber-physical system, CPS, threats like Stuxnet.
Exactly. Attacks that bridge the cyber and physical worlds, causing real-world damage. But also more common attacks, data spoofing, eavesdropping, ransomware, social engineering, tricking employees.
Denial of service, DOS, DDoS, attacks, shutting things down, man-in-the-middle, replay attacks.
Yep, plus physical threats like attacking power grids and specific data-related threats, stealing designs, unauthorized disclosure, weak passwords, poor device management.
Exploiting vulnerabilities in the hardware, software network, or even just poor management practices.
All of the above. Weak points can exist anywhere in the chain.
So, data protection strategies, what are the basics?
The core principles. Confidentiality, only authorized access. Authenticity, verifying the source. And integrity, ensuring data isn't altered. The CIA triad of security, essentially.
And encryption is key, symmetric versus asymmetric.
Fundamental. Symmetric uses one shared key, fast, but key exchange is tricky. Asymmetric uses public-private key pairs. More complex key management, but easier secure distribution. Both have roles.
What about message authentication codes, MACs?
Like a digital seal. Ensures both data integrity, it hasn't changed, and authentication, you know who sent it, using a shared secret key. Very important for verifying commands or data streams.
And data leakage prevention, DLP.
Systems designed to monitor and block sensitive data from leaving the controlled environment, whether accidentally or maliciously, using techniques like document classification to identify confidential info.
Okay, one more, core tech, blockchain. Not just for Bitcoin.
Not at all. Its core characteristics are incredibly valuable for Industry 4.0.
Like being a distributed ledger, shared record across many computers.
Right, and tamper-proof immutable. That cryptographic linking of blocks makes it incredibly hard to alter past records secretly. Plus, it's decentralized. No single point of failure or control.
So its role in Industry 4.0 is about trust, traceability.
Exactly. Enhancing traceability in supply chains, providing auditability for processes, creating trusted data provenance, knowing for sure where a component came from or that a measurement hasn't been faked.
How does it achieve agreement without a central authority? Consensus algorithms.
Yes. Different methods like proof of work, co-solving puzzles, Bitcoin's way, energy-intensive, proof of stake, POS, validation based on stake ownership, more energy efficient. Others like proof of activity, POA, or proof of burn, POP, exist too, all ways for the distributed network to agree on the truth.
And applications beyond finance, supply chain management.
Huge potential there. Transparency, reducing fraud, Also, smart property registration, even government services enhancing efficiency, reducing red tape, and blockchain IoT, securing device interactions.
Challenges still exist, though. Scalability, privacy.
Big challenges.
Yeah.
Scalability transactions per second can be limited. Potential privacy leakage on public chains if not managed carefully. Issues like selfish mining. It's powerful, but not a magic bullet for everything.
Okay, we've covered the tech. Now let's talk about the people. Humans and machines, the Industry 4.0 confluence.
A critical aspect. This isn't just about tech. It's fundamentally changing human work.
The shift away from the dangerous, dirty, difficult, dull tasks.
Exactly. Robots and automation take those over, freeing humans for higher-value roles, needing expertise, creativity, problem-solving, oversight. It's about augmentation, not just replacement.
Because human intelligence and intervention are still essential, right? For safety, security, handling unexpected things.
Absolutely paramount. Humans bring adaptability, ethical judgment, intuition that AI lacks. We need humans to oversee, manage, and work alongside these systems. Trust is also key, using things like explainable AI, XAI, to understand why an AI makes a decision helps build that trust.
But there are challenges in human-machine interaction, HMI, like how machines perceive things differently.
Machine perception is binary, literal.
Yeah.
Humans perceive nuance, context. This difference can lead to misunderstandings or errors in interaction.
And mismatch of expectations, what the user wants versus what the system does, or how it presents info.
Yes. Designing interfaces that align user actions with system capabilities and present information clearly and intuitively is crucial for effective collaboration, bridging that gap.
So how do we foster that synergy? Design for a human-centered Industry 4.0.
That's the goal. Using things like engaging training modalities, augmented reality AR, and virtual reality VR are powerful tools here. Immersive, safe training for complex tasks.
Like learning to operate dangerous machinery in VR first.
Exactly. Build skills and confidence safely. Gamification, too, using game mechanics to motivate learning or task completion. But it needs careful design based on user interest and real goals, not just adding points for show.
And building trust in AI systems is ongoing work, using explainable AI.
Vital. Helping users understand when to trust AI and why. XAI tools that make AI decisions transparent are key to fostering that confidence and enabling true partnership. Opening the black box.
The ultimate vision isn't human replacement, but collaboration.
Precisely. Humans and machines working in tandem, leveraging strengths, ensuring humans feel empowered, not excluded, ideally leading to better jobs, better work-life balance, alongside the efficiency gains.
Okay, let's bring this to life with real-world applications and impact. Where is Industry 4.0 making waves already? Let's start with healthcare.
A massive area, driven by needs like managing chronic diseases better, improving system efficiency, reaching rural areas.
IoT solutions like remote health monitoring seem huge here. Wearable sensors sending data.
Yes, collecting vital signs continuously, allowing early intervention, emergency alerts, personalized care adjustments, moving towards healthcare 4.0 care tailored to the individual's genetics, lifestyle.
Tracking patients or assets in hospitals, too.
Right, and providing alerts for critical conditions.
And ML for disease detection, using algorithms on patient data.
Absolutely. Applying models like SVM, ANNs to data sets for earlier detection of cancer, heart disease, etc. Powerful diagnostic support tools for doctors.
And even logistics within hospitals, finding equipment faster.
Improving supply chains, tracking assets, making the whole operation run smoother.
What about manufacturing and supply chain? We've touched on this.
It's transforming core operations. Optimizing design, improving processes, predicting disruptions, real-time monitoring.
Predictive maintenance is the star here, using DTs and AI to foresee failures.
A huge driver, predicting CNC machine breakdowns, minimizing downtime, shifting from reactive to proactive.
And intelligent logistics, P&G, using big data.
Streamlining supply chains, optimizing planning, using data for faster, better decisions across global operations.
Moving to smart cities and vehicles, smart grids.
Networked meters for energy, water, gas. Enabling efficient utility management, load balancing, leak detection. Much smarter than traditional grids.
Smart vehicles using sensors for driving analysis, insurance, fleet management.
Yep. Analyzing driving habits for safety, personalized insurance rates, optimizing routes and maintenance for fleets.
A critical application. Orbit is getting crowded. SCCS uses multiple subsystems.
Traffic identification using cameras.
Density evaluation mapping congestion.
Risk assessment calculating collision probability. Safe trajectory planning finding escape routes.
And the heads-up display, Showing pilots the info?
Right, a comprehensive system using IoT, imaging, modeling, and smart displays to keep spacecraft safe. Crucial as space gets busier.
And digital twins for smart city planning, too.
Mhm.
Modeling traffic flow, infrastructure.
Yes, optimizing urban environments on a larger scale.
Finally, retail and e-commerce. Recommendation systems. RS.
Essential now. Filtering information overload, suggesting relevant products, boosts sales, customer loyalty.
Using different approaches. Collaborative filtering, people like you liked. Content-based, you like this, try this similar thing.
And hybrid approaches combining both. Trying to overcome challenges like the cold start problem, new users items, and data sparsity. Deep learning is helping here too.
Real examples, Walmart analyzing trends, Netflix's recommendation engine driving viewing, and even production.
Exactly. Using massive data analysis to personalize the customer experience and optimize business strategy. It's core to their success.
Okay, as we wrap up, let's revisit the big picture, the overarching challenges and the future outlook.
Definitely. Key cross-cutting challenges persist. Scalability is huge, managing the sheer growth in devices and data without systems breaking down.
Energy consumption for all those sensors and devices, keeping them running efficiently.
Critical. And data standards and processing, ensuring data quality, managing the processing load, having consistent standards for things like digital twins.
That lack of standardized modeling approaches hindering interoperability.
Yes, makes integration harder. And overarching everything. Privacy and security, protecting this vast amount of sensitive data from constant cyber threats.
But the future looks promising. Lots of research.
Absolutely. Promising avenues include deeper modeling of cyber-physical fusion for smarter DTs, more advanced prognostics in health management, PHM, even for human well-being.
Improving data accuracy through techniques like data fusion.
Developing more human-inspired AI transparent collaborative systems that enhance human work, not just replace it. Synergizing AI, HCI, and Industry 4.0.
High-fidelity dynamic models for complex robotics using AI-powered DTs.
Integrating more with AR/VR for enhanced interaction. And the continued evolution of cloud-based analytics becoming more flexible, real-time, secure, and ethically aware.
What an incredible landscape. So to recap, Industry 4.0, fueled by intelligent analytics, is this profound merging of physical and digital, driven by tech like DTs, AI, robotics, big data, blockchain, IIoT.
And it's not just theory. It's actively reshaping manufacturing, supply chains, healthcare, even how we manage space travel. It's happening now and accelerating.
It really is. So maybe a final thought for everyone listening. As these lines between human and artificial intelligence keep blurring, think about that synergy. What truly new possibilities emerge when our physical world gets seamlessly woven together with an intelligent, constantly learning digital replica?
A responsive, adaptive world. Maybe even self-healing in some ways. It opens up fascinating questions about the future.
Absolutely. And remember, this revolution isn't just for tech insiders. It touches every part of our lives. So keep exploring, keep asking questions, and keep an eye on how these intelligent systems are redefining our future. Thanks for diving deep with us today.